Hello, my name is Rusty Bascom. I'm a principal engineer with Electrical Consulting Engineers located in the United States. Today I'll be summarizing for you our paper, Application of Horizontal Directional Drilling and Other Trenchless Methods to Electric Power Cable Installations. The co-author for this paper is Jim Williams from Brierley Associates. At the conclusion of the presentation, please use the email address shown to contact me if you have any questions. Underground power cables are an integral part of most utility systems. Most of these systems are installed using conventional open-cut trenching from the Earth's surface. However, there are often segments along the cable route that prohibit use of open-cut trenching for various reasons that will be summarized on the next slide. This paper summarizes the types of installations that may use trenchless methods and gives a description of each of the methods along with some of the associated design considerations, including both electrical and civil design factors, such as grout selection, casing material selection, and construction method. From the standpoint of power transmission and distribution, underground cables are used where overhead lines are not possible or practical. Trenchless methods are used where open-cut trenching is not possible to install those underground cables, including situations such as high density of shallow pre-existing utilities, where open-cut would be too disruptive to the stakeholders, where there's the possibility of contaminated soils that would have high disposal costs, a project located in archaeologically or culturally significant areas, to facilitate crossing the shore zones for submarine cable installations, in environmentally sensitive areas, and for water crossings where the distance of the crossing is within the range of the trenchless technology. The civil design for trenchless methods involves a careful evaluation of the route, considering the geological conditions and soil types along the proposed drill path. Ideally, soil borings are collected every 50 to 100 meters along the route, usually offset by 3 or 4 meters to avoid creating paths for inadvertent returns, and that information is then assessed to design the drill path. The drill path is then selected by the civil engineer. Most of the time, civil engineers prefer a deeper installation depth because there's more stable geological strata and better consistency. However, cable engineers prefer a shallower depth, usually for better ampacity. An important consideration for selecting a drilling method is the laydown area, because this can be a significant factor in where the construction methods may be applied. We'll now summarize the types of trenchless technology. Pipe jacking is the first type, which utilizes a launching pit and receiving pit. Between the two pits, a casing is advanced as the face of the casing is excavated using an auger or hand digging, and the spoils are moved back through the casing. Microtunneling is a related technology, except the entire process is mechanized and operated remotely. For both methods, the distance that can be crossed is limited by the frictional forces of advancing the casing, but typically no longer than 300 meters. Microtunneling does permit some minor changes in direction, unlike pipe jacking. An advantage to these methods is that the laydown area is relatively compact on either side of the crossing. A box culvert is a similar technology, except everything is done by hand excavation and is permissible in areas that are very compact where there's other utilities present. Another type of trenchless technology is horizontal directional drilling, or HDD, which is borrowed from the petroleum and natural gas industries. The equipment laydown area for horizontal directional drilling is far more substantial than the other trenchless methods, but has the advantages of being able to steer and change direction, as well as being able to go longer distances. The civil engineer designing the horizontal directional drilling project reviews the geotechnical borings from the route and determines a drill path that is most suitable for the project. During the drilling process, a pilot hole is created along that drill path, and the pilot hole is enlarged through a process called reaming until the required opening size is achieved. Once the opening is created, the casing pipe can be pulled back through that opening. The casing pipes themselves consist of either high-density polyethylene, fusible PVC, or steel, which all have an impact on the cable system design. Horizontal directional drilling used for underground power cable projects typically is limited to about 2.5 kilometers, based upon the amount of cable that can be pulled into the opening after the civil work has been completed. Pipe bursting is a technology that's recently being considered for use for underground power cables. With this method, an existing conduit or pipe is intentionally fractured so that a new pipe or conduit can be pulled in through the existing opening. Then power cables can later be installed once the new conduit or pipe is placed in the ground. Casing material selection is an important design parameter for both civil engineering and electrical engineering. Civil engineers often prefer steel because it has high compressive strength and tensile strength limits, while cable engineers might prefer a plastic casing materials such as high-density polyethylene or fusible PVC because it does not introduce additional heating losses that would impact ampacity. Reinforced concrete pipe and resin-reinforced epoxy pipe are other materials that could be used for certain applications such as pipe jacking and microtunneling. The table on the following page summarizes the various casing material characteristics. This table summarizes the characteristics of various casing materials used for trenchless technology on underground power cable systems. Some of the characteristics are important from an electrical engineering design because they impact the cable rating or ampacity. Others are very important from the civil engineering design because of their mechanical properties. As the table illustrates, certain materials are only appropriate for specific types of trenchless methods, and this is part of the selection process that's used by the civil engineer and the electrical engineer in designing these types of installations. The annular space between the conduit and the inside of the casing is an important design parameter from the standpoint of ampacity. From electrical design, this area should be filled with a high-density material that provides good heat transfer. From a civil engineering design, it's desirable to have materials with low pumping pressures, which often involve high concentrations of water and bentonite clay, which are often in conflict with the low thermal resistivity characteristics that are desirable from a cable engineering standpoint. The table at right shows some of the characteristics of various grout materials. The electrical design of underground cable segments utilizing trenchless technologies is often focused on the cable rating, and the methods used to evaluate ampacity, including the 1957 paper by Nair McGrath and IEC 60287, are applicable provided the appropriate parameters are utilized in the evaluation. This includes consideration for the configuration of the cables and the casing materials being utilized for the trenchless method. Steel casings require a special analysis because of the ferromagnetic properties of the steel and the associated impact on the losses. Mutual heating effects are also exaggerated at the deeper installation depth, as well as the ambient temperature and moisture content of the soil that could impact the thermal parameters used in the ampacity calculations. Trenchless sections may be longer than conventional open cut sections, and this could impact the bonding systems for underground cable circuits, especially where cross bonding or single point bonding are used because of the impact on induced voltages and currents. Also, in situations where steel casing is being utilized, this could impact the effectiveness of any corrosion protection systems associated with the cable system. An appropriate design for power cable segments to be installed using trenchless methods must consider both the civil and electrical engineering design constraints. Soil characteristics are important for the civil engineer to determine the soil mechanical properties and the geology in order to select the best drill path, and the electrical engineer must understand the soil thermal resistivity and ambient temperature at the expected installation depth in order to calculate cable ratings and select the conductor size. Both civil and electrical engineering design constraints impact the materials selected for the casing and grout to fill the annular space within the casing. Various industry references, including CIGRE Technical Brochure 770, Trenchless Technologies, are available as resources to help with this design process.